So this is a cylinder. Well, he said it's a tube. The tube filled with nuclear material. So really, when you think about this, it's as if he's saying there is this material like this, aluminum tube. And so it's filled with this nuclear material that's generating the heat. But we had no idea about the thickness of that tube or the K of that tube, right? We don't really know any detail about how thin this tube is, whether it's 1 millimeter thick or 5 centimeters thick, and what its K. We don't know. Or even the material. Actually, it's supposed to be aluminum, but he didn't even say what is the material, right? Okay, and the fuel pen, I showed you a picture of this in the slide, but he said this is 0.16 meter in diameter, and the surface temperature is measured using a thermocouple as 550. Well, is the surface is here, or basically we don't know the thickness, so it's just the surface temperature, and it's so thin that there is no really difference between the outer surface and the inner surface. But he said that the surface temperature is 550. The material conductivity is 2.5, so he gave you K over here. And the rate of heat generation, so that's E dot generation. That's watt per meter cube. Determine the maximum temperature in the nuclear fuel pen. So you can start this problem from scratch, saying that well, I had this cylinder, and the radius R start from 0 all the way to R naught, or R surface. What did we call it? R surface? R naught. R naught. And the temperature here, I don't know. Actually, he's asking for it. He didn't really ask for it. He said, what's the maximum temperature? Guess where is the maximum temperature? This is a rod generating heat. And he is generating heat, okay? So the heat is coming from within to the outside. So chances are the maximum is going to be not really on the surface. And so Ts is given to us, and T0, or actually, let's call it T maximum then. T max is not given. So you can start this problem from scratch, meaning you start with the general equation of conduction, you cancel the unsteady term, and you would say, well, I will integrate this equation twice. And when I integrate this equation twice, I need two boundary conditions. One of them is here. The other one would be, where else? I mean, that cylinder starts from R equals 0 to R equal R surface, right? There is no other place to get the boundary condition except in the center line and at the surface. Right? It's as if I'm telling you there is a wall insulated from one side, and and it's generating Q dot or E dot per unit volume, and here is Ts, and find for me the temperature distribution. Well, when you integrate this twice, there is no place to get the boundary condition except at the two edges. There is nothing in the middle so special that you can put your hand on its temperature or its gradient. So for that cylinder, if you are integrating from scratch, one boundary condition is over here. The second boundary condition need to be there. It's not that T equal 700 or 800 in the center line, because we don't really know what's the temperature at the center line. Actually, we are required to calculate that. So what is the other boundary condition? Delta T over delta X equals 0. That means partial T, right? Partial T, partial X at R equals 0 is 0. What's your name again? Robert. Robert is saying that the gradient at the center line is 0. Or basically saying that the temperature profile is probably going to be like something like this. That it would basically peak in the middle. So whether he think it's because this is the maximum, that's correct, or whether he think because of the symmetry, that's correct, or whether he could think also that at the center line, basically the heat going to the right and to the left is exactly the same. So it's kind of, there is, ouch. It's really as if there is really no flux going in the outside the center line because of the symmetry. It's not going to the right or to the left. Anyway, it's because of the symmetry. The Q here is, or the partial T partial X is 0 at the center line. Okay? So you can do through this. You can go through this and come up with the answer, or you can just open the textbook. And you will find out they already solved this problem. All right? It's already solved for us. And the exam is open textbook. And the equation is here. And so whether you just try this equation or you drive it yourself, there are 2 points to get there. This is the equation for a cylinder with uniform heat generation in the middle. Right? This is T at any R. You give me the R, I give you the T at this R. So if you give me R equal R outside, the outer surface, it will be R naught minus R naught. This term go to 0, and T will be Ts. Right? You give me R equals 0. R equals 0 mean the center line here. Then you will get Ts plus this guy. Right? And also if you go through lecture notes, you'll find out that he said for a pipe with heat generation or an electric resistance with heat generation, that term over here was the maximum that we could expect, the maximum temperature difference on top of Ts. And we had this expression for cylinder, for a sphere, for a plane wall with insulated center line. That is the maximum temperature on top of Ts because of the heat generation. All right, so what's remaining is he would like to get the temperature at 2 locations. Right? Did he ask? No, determine the maximum temperature in the nuclear fuel rod compared with temperature at R 0.004 meter. Right, at 2 locations. So first he wants the maximum, and so by looking at this equation, you can tell that the maximum would be when R is 0, because this term, to make it go up, you want R to be as small as possible. Right? So the maximum will happen when R go to 0, and that would be 966. Just cancelling this R, or putting this R equal to 0. And at R equal 0.004, so that would be something like here, because the radius is 8, right? The whole thing is 16, and so the radius here is 8. 8 what? 8 millimeter, right? So he would like it at 4. So at 4, all we have to do is just substitute for R equal 4. And you get the temperature as 862. Right? So this number is 0.5, this number is 0.5. Coming to this equation is 2. Substituting in the equation is basically worth 2 points. Questions? Does this make sense? You can drive the equation yourself again, or you can just, if you find it in the textbook, you can just grab it there. All right?